In this video, I will explain on some of the principles of electrocyclic reactions. So in electrocyclic reaction, there are two types of mechanism that is involved, which is ring closure and ring opening. If you look at the example here, so the first example is a ring closure where you have a polydiene polyene. When it is heated, it will form a new product or a closed ring. So this new product has new sigma bond, and normally the product has one fewer pi bond than the reactant, meaning if you have 3 pi bond here in the product, there will only be 2. Okay, another mechanism involves ring opening where you have a cycloalkene. So when it is heated, the ring will open and give you a polyene. So in ring opening, the sigma bond at this part will be broken, and then it will give you a new product that has one more pi bond than the reactant. So you see, if it is ring closing, less one pi bond. If you have ring opening, it has one more pi bond. Okay, in electrocyclic reaction, the reaction is completely stereoselective, meaning one condition can only produce one type of isomers. So in this case, if you have a trans product like this, a trans reactant like this, when it is heated, it can only give you a cis product, meaning that there is no mixture of cis and trans product. It will specifically give you a stereoisomer, which is the cis. Okay, if you look at another example here, so when you have the same compound or the same starting material, but it undergo a different type of condition, so it undergo UV, so the reaction will give you a trans product, okay, which is only trans product. There is no mixture of trans and cis product. So we were thinking of how this reaction can give us a specific stereoisomer. This is how it happens. So in order to form new sigma bond in the electrocyclic reaction, the pi orbital at the end of the conjugated system must overlap head to head. So normally, in this case, ring closure is con-rotatory. If you look at the arrow here, con-rotatory meaning it is one clockwise and another one is also clockwise. Or if this is anti-clockwise, this is also so if this is clockwise, then it will become clockwise as well. You need to rotate at the same clockwise. Okay, if it is disrotatory, meaning one of these p orbital will move clockwise and another one will move anti-clockwise. So this movement is what we call as disrotatory. Okay, so how do we know if it is giving us a con-rotatory or disrotatory? So first, we need to focus on the HOMO of the acyclic conjugated polyene. So this is in the case of we want to do ring closing, yeah? So if we want to focus on the ring closing, we need to focus on the HOMO of the starting material, which is the acyclic conjugated polyene. First, we need to examine the p orbitals on the terminal carbon of the HOMO. We must make sure that it's terminal carbon of the HOMO, where the carbon has the double bond, yeah? Okay, and then the third step, determine whether like faces of the orbital are on the same side or opposite side of the molecule. Okay, there will be two possibilities. The first one if the light phases is on the same side, while the light phases on the opposite side. Okay, in order to make sure an electrocyclic can occur, we need to make sure that the light phases of orbital can overlap to form a bond. So in this case, the reaction is symmetry allowed, meaning we can do the reaction. But in the case of there is an orbital with opposite phase, so the electrocyclic reaction cannot occur, and this reaction is what we call as symmetry forbidden. Therefore, in order to form a bond, the terminal C carbon must rotate so that the light phases can interact to form new sigma bond. Okay, there are two modes of rotation. The first one is when the light phases of p orbital are on the same side of the molecule. So the two orbital must rotate in opposite direction, which is one clockwise and one counterclockwise. Okay, if you look at the light phases, the red color p orbital, in order to make them overlap with the same color here, so we need to turn one clockwise and another is counterclockwise or anti-clockwise. Okay, in this case, the rotation is called this rotatory. So you need to turn this here, then another one is at the opposite direction. So what happens after rotation? You will form a new bond where this, when you turn it here, so this blue orbital can go up here, and then another blue orbital will go up here, and then they will form a new sigma bond. But when light phases of the p orbital are on the opposite side of the molecules, so the two orbitals must rotate in the same direction. Either it is both clockwise or both counterclockwise. Such rotation is what we call as con-rotatory. Okay, in this case, the light phases of the p orbital are opposite. So to make sure this blue can overlap with this blue, we need to turn it using con-rotatory rotation. So in this case, we bring this p orbital here and then this one also moving clockwise. So what will happen is that the blue one will come in the middle. Okay, the blue one here will come in the middle. Okay, this is the blue one. Okay, it is con, so it will give you a new sigma bond. This is in the case of ring closing. Okay, so this mechanism can explain the stereochemistry observed in electrocyclic reaction, where first we need to examine the symmetry of the molecular orbital, which is the most loosely held pi electrons. And thermal reaction, for thermal reaction, we need to consider the HOMO of the ground state electron configuration. And the number of double bond in the conjugated polyene will determine whether rotation is con-rotatory or dis-rotatory. Normally, when I memorize this, for ring closing, when it is thermal with odd number of electron, so normally the rotation is dis-rotatory. If it has even, if it is thermal, but then the number of the polyene is even, the motion will be con-rotatory. This is how I memorize the rotation. So if you have the condition, it is UV and it is odd, so it should be con rotatory. Then if you have UV, it is even, so it should be this rotatory. Okay, what I usually tell students is I will just think of this and then I will sort out the rest of the rotation for different types of polyene and different types of reaction condition. Okay, we take a look at the example here. So different condition will give you different types of product. So in this case, if you have a cis product, a cis reactants, so we undergo electrocyclic reaction with thermal heating, and then you will get a trans product. Okay, but if you change the condition, the same starting material, you change the condition into UV, not using thermal, but you use UV to activate the reaction. So what you will get is a cis compound. Okay, next example, if you have this type of starting material, which is the cis. Okay, under thermal condition, okay, you look at this only has two diene. So when it has two diene, you know that just now I said if it is thermal and the number of polyene is even, so it should be con-rotatory. So the rotation here is con-rotatory, which will give you a cis product. So in this case, we have UV. So in this case, it will be UV because it is even. So the rotation is this rotatory. So it will give you a trans product, which is different from the first reaction where you use just heat. Okay, another example, if we have 2E4E hexadiene. So by using thermal, you can produce trans reaction, trans product, but when you use UV, you can get cis product. Okay, in the next video, I will explain on detail how is the mechanism of the formation of these products. Okay, stay tuned.